Bismillahirrahmanirrahim. In this lecture, we will discuss sum of tensors, product of tensors, two tensors, some examples, then transpose, trace, and identity tensor. Also, dyadic product will also be discussed. Now, let us start with sum of tensors. That if we have two tensors T and S, then their sum will also be a tensor, and we define this transformation, that this sum transformation, which is sum of two tensor, is in this way: 2b4.1, that T plus S will, when T plus S will act on A, it will give us TA plus SA. Now, using this T plus this definition, we can show that this sum is a tensor. So you will show this, that how it is a tensor. Now let us find its components. Now here we are using the definition of the components of tensor, that if you have tensor T and its components Tij will be equal to Ei dot Tej. In similar fashion, you can write, if you are denoting this somewhere by W, then you can write Wij, any ijth component of sum, equals to Ei dot T plus Sej. T plus S act on Ej. So use definition. Here you can write Tej, Ei dot Tej plus Ei dot Sej. This will be equal to Tij and this is equal to Sij. So components of W is the sum of the components of T and S. So ijth component of W will be the sum of ijth component of T and S, and this is the matrix form. W is equal to T plus S. Now we will see the product of two tensors. Suppose that you have two tensors S and T and any arbitrary vector A. Then TS and ST product are defined to be linear, to be transformations in this way, that these are transformation. And how they are defined? They are defined that TS acts on A will give you T of SA, and when ST acts on A will give you S of TA. This product is a tensor. So you need to show that how this product is a tensor. So you need to verify two properties of linearity. Here again we are finding the components of this product. So by definition, so we have to go through by definition. TS ij, ijth component of this product, equals to Ei dot TS Ej. Now here we will use definition of this product. T of Sej will be equal to, here we are using Sej. Sej equals to Smj Em. No, this is from your third lecture or second lecture, I think, in which we have discussed components of tensor, that how we can find the components of tensor. From there we are writing this Sej equals to Smj Em. Now this is scalar, so you can take this out. So Smj Ei dot Tem, this is equal to Tim, any imth component of T, Ei dot Tem. So this is Tim Smj. So Ts Ij equal to Tim Smj. There come, and if this is St, then this will be equal to this. Then any ijth component of Ts will be from this equation, 2b5.3, Tim Smj. You can see that T is at the first position and I index is at the first place of this product. So I will be the first index of T, and here J is the second position, so J is the second index of S, and MM, dummy index. Here you can see that Si and Tj. Here S is at the first position of this product and I is the first index of this product, so Si and T is the second element of this product and J is the second index of this product, so J would be the second index of T, J and MM. In matrix form this can be written as, and we can easily see that this is not commutative, product is not commutative, as matrix product is not commutative, so in general TS can't be equal to ST. Let's see the associativity of three tensors. Suppose we have T, S and V three tensors. T of S V acts on A will give you by definition of product. T is 1 and this product will act on A. T of SV at A. T outside and SV acts on A. Again you are using product here, S of V of A. Now if TS and VA, then it will give you T of SVA. You can write one step before this, TSVA, and that step will be in this form, TS bracket V whole bracket outside A. That will be equal to this thing, and this will be equal to this T of SVA. So you can see their right and left side are equal. This and this are same, so you can write T of SV equal to T of SV. So with the help of this you can find any integral positive power of T square, T cube, T4, T5, like this. Now in this example you are asked to find the product of two tensors. First you will be asked to find the matrix of R and S rotation and reflection, then the matrix of their product, then how that product will transform any vector. Let R be a matrix, let R be a rotation through an angle of 90 about x3 axis. Find the matrix R. You can use the example this. You can use the example in which you have written the matrix about x3 axis with an angle of theta. That is, R is equal to cosine theta E1, RE1 equals to cosine theta E1 plus sine theta E2, RE2 equals to minus sine theta E1 plus cosine theta E2, and RE3 equals to E3. So here theta is 90, so cosine theta E1 cosine 90 is 0 plus sine theta sine 91, so we have only E2, so RE1 equals to E2. Similarly RE2 equals to minus sine theta minus sine 90 minus 1 plus cosine of 90 E2, that will be 0, so we have RE2 E2 equals to minus E1, and similarly RE3 is equal to E3, and we can write this matrix. This is for rotation about x3 axis with an angle theta is equal to pi by 2. Now in B part, what we have to write rotation for 90 angle about x1 axis. So x1 will be fixed, SE1 will be E1, and similarly as you have calculated this R, you can calculate this S while taking rotation about x1 axis. So this is 1 0 0 0 0 minus 1 1 and 0 1 0. Now in third you have to calculate find the matrix of tensor that correspond to the rotation A then B. First A then B. It means that you have to calculate SR. First A then B, and in D simply you have to calculate this product, and in D you have asked to find first B then A, so first S then A, RS. And in E part you have to use this SR and RS to find the transformed vector. R is given, R is 110, so you have to find both using C and D, find new vector, transformed vector. So for C you have to use this SR, acts on R, and for D you have to use this RS when acts on R, and you will have the results. Do the questions from the exercise which are related with this topic. And do the transformation and find that transformation matrix. As I have, this is written S here, you need to find this. I have explained this, and with the help of this you have to find this S. That is SE1 equals to E1, that we are taking rotation about x1 axis. SE2 will be equal to cosine of E2 dash, cosine of angle between E2 dash and E1 plus cosine of angle between E2 dash comma E2 and plus cosine of angle between E2 dash comma E3. Outside we have E3. So first term will be 0 because angle between E2 dash and E1 will be 90. And second term will also be 0 cos 90, and third term we have cos 0, E2 dash between E2 dash and E3, cos 0 1. Similarly you will find this E3, this SE3 will be equal to minus E3. You can find this. First you will draw this axis on a paper, then from there you can write this thing. Transpose. Now if T is a tensor, then transpose of T is defined to be a tensor, and this transpose will satisfy this equation A dot T B is equal to B dot transpose of T A. If we are saying that this is transpose of T, then this will satisfy this equation. Now you have to show that how this transpose is a tensor. This is the components. EI dot TEJ equals to EJ dot transpose of EI. Now this is simply TIJ, this is a TJI transpose. With the help of this you can find the components of transpose. That T11 transpose will be T11, second component T1 transpose will be T21. Similarly third, fourth, fifth. It means that matrix of transpose of tensor will be equal to transpose of that matrix. Transpose of that matrix. This is the matrix. That is the matrix of this matrix of transpose of T, the transpose of T. Here we have shown that transpose of that if we have taken 2 times transpose, then we have again T. That transpose of transpose will give us matrix, renal matrix. This is from definition, that A dot transpose of T B will be equal to B dot transpose of transpose A. This is the definition 2B 6.1. Now we can write B dot. Now we can write this B dot TA equals to A dot transpose of T A dot transpose of T B. That B dot TA equals to from before this we have one step. B dot TA equals to A dot transpose of TB, and that is equal to this. So we can write B dot TA equals to B dot transpose of transpose equals to A. So from here we can write T is equal to this, and also you can have this relation, and this is the transpose of the product equals to the product of transposes in their reverse order. Similarly, you can generalize this thing, that if you have more than two tensors, you can write this. No, dyadic product of two vectors. We have defined, if you have two vectors, then you can define dot product, scalar product. No, dyadic product of two vectors. How will you will define the dyadic product of two vectors? No, dyadic product of A and B will be denoted by this AB, and this is a transformation. And how we will define this transformation? We will define this transformation in this way, that when this transformation acts on a third vector C, then result will be in this form, A into B dot C. So this dyadic is a tensor. So this is shown in here, this is shown here, simply using the definition of this product, this dyadic product. You can show that this is equal to this. Now here we have calculated the components of this dyadic product. Simply you are saying that W is equal to AB, you can write Wij equals to EI dot Wej, or instead of W you will use AB. Here we will use the definition of this. You can write this thing. Now B dot Ej is Bj, and EI dot A is AI, simply. So Wij is equal to AI Bj. So it means that components of dyadic product will be that components of this AB can be written with the help of this equation, that W11 will equal to A1 B1, W12 equal to A1 B2, and this thing in matrix form can be written in this way, that W is equal to A1 B1, simply A B, column matrix, row matrix. Now here we have written 9 dyadic products with the help of base vectors, 3 base vectors, E1, E2, E3. So with the help of these 3 base vectors, E1, E2, E3, you can have 9 dyadic products. That E1, 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 E2, E1, E3, 3, then E2, E1, E2, E2, and E2, E3, 3, and with the help of E3 you can have again 3. And keep in mind that AB not equal to BA, that you can have E1, E2, and find E2, E1 that will be different from this. So we can write this any tensor T in the linear combination of these 9. That T is equal to T1 E1 plus T12 E1 E2. This is the product. This is 3 by 3 matrix, left hand side and right hand side. T11, this is 3 by 3. T12 element, this is 3 by 3, sorry, up to this, and whole this can be written in addition notation in this way, Tij Ei Ej. No, trace. So trace is a scalar number. You can define the trace of this dyadic product AB is A dot B. You can see that, you know that trace is simply the sum of diagonal elements, A1 B1 plus A2 B2 plus A3 B3. So it would be A dot B. A dot B is basically A1 B1 plus A2 B2 plus A3 B3. So furthermore, the trace is defined to be the linear operator. This is basically linear operator. So keep in mind that trace is not a tensor, not a second order tensor. It's scalar. It is a scalar number. Trace is a scalar number, so it is a 0th order tensor, but it's a linear operator, that this will be equal to this. So trace of T can be written as trace of T, and this T is equal to this trace of this, and here we have we are writing Tij outside because this is linear, and Tij are simply the scalar numbers, trace of Ei Ej. So trace of Ei Ej with the help of this is Ei dot Ej delta Ej. So if you calculate this, you will have Tii. So trace of T is Tii. This is this, and trace of transpose of T is again trace T. This is you need to show this, that trace of transpose is equal to trace of this. Calculate trace of transpose like this. So first you have to write transpose in this way, as you have written T in this way. Then you can take the trace, and you will see that it is again T11 plus T22 plus T33. This is the simple example in which they are showing that trace of AB equals to trace of BA. A and B are two tensors, second order tensors. Let C is equal to AB. You can write the components of Cij equals to AIM BMJ, and trace of AB will be equal to trace of C, and trace of C is CII. What is CII? AIM BMI. No, let us D is equal to BA. Components of Dij equals to this. Trace of BA is equal to trace of D, that will be DII, and DI from here BIM AIM. No, they are same because I and M, they both are dummy in these two equations 1 and 2, so they are same. So it means that trace of B is equal to trace of AB. No, identity tensor. Now, what is identity tensor? You know that what does this mean? That identity means that if this tensor acts on any vector A, then the result will again that vector. That means IA is equal to A. So IE1 is equal to E1, IE2 is equal to E2, IE3 is equal to E3. So from this you can write its components 1 0 0, 0 1 0, from here 0 0 1. And also in this way you can write Iij is equal to Ei dot Iej, and this is Ej because I is identity, so Ei dot Ej is equal to delta Ij. No, this is any example that write the tensor T defined by the equation, that if you have a tensor T and it defines like this, it is defining like this, T is equal to K times A, K is constant and A is arbitrary vector, then write this T in terms of identity tensor. So how can we do that? We know that T is equal to Ka, and this can be written as Kia. So from here you can write T is equal to Ki. That form of T is the K times identity, and obviously Tij is equal to K times delta Ij. K will be remain same because it is a constant, and components of I is delta Ij and components of T is Tij. Now if there is identity, so there can be defined inverse of tensor T. So if you have this St is equal to I and Ts is equal to I, then we can say that S and T are inverses of each other. And you know that for inverse to be exist, we must have determinant not equal to 0, and if determinant is equal to 0, inverse can't be defined. And you can write that T inverse T is equal to T inverse is equal to identity, that if T and T and minus 1 of T are the inverses of each other. And you can write this T inverse T is equal to T inverse is equal to identity. And this you have to do, that inverse of transpose is equal to transpose of inverse. These are the exercise. And if the inverse exists, then you can write this, that T is equal to Ta is equal to B equals to A, and A is equal to inverse B. Then you have this reciprocal form if the inverse exists. It indicates that the invertible there is 1-to-1 mapping of vectors A and B, that there is only 1-to-1 mapping. That on the other hand, if the tensor T does not have inverse, then it means that for any vector B you have more than one pre-images. For example, we know that T is a dyadic product CD. Let us write dyadic product CD as T. and we know that this inverse does not exist because its determinant is 0. So now we will see that this inverse does not exist, and we will see that for any vector b which is image, that will have two pre-images, more than one pre-image, in the sense of this, that any two different types of vectors will be transformed with the help of this dyadic product on the same vector b. I'm using the word pre-images in the sense that that we have two different vectors, and T dyadic product acting on those two vectors and will give you the same vector. So it means that that will be not one to one. Let's see, T is equal to this, use T CD, and by definition C of T dot A, we are saying this as B. Now again we have taken a vector H in such that is perpendicular to vector D. We have vector H which is perpendicular to vector D, that is D dot H is equal to 0. Let's take the transformation of this A plus H. A plus H. H, what is the condition of H? H is basically perpendicular, this is perpendicular on the D. So when T acts on A plus H, it means that CD is acting on A plus H, will give you, by definition, what will give you? C dot CD, C outside, D dot with this, D dot with this sum, as definition of dyadic product. It means that C outside, inside the bracket, C dot A plus D dot H, inside D dot A plus D dot H, and D dot H is 0, so we have C into D dot A. This is the again the same B which is written here. So it means that we have two different vectors, A and A plus H. They are transformed on the same vector. This is what we are saying, that if inverse exists, then we have one-to-one mapping here. T is equal to B and A is equal to T inverse B. And if inverse does not exist, then it means that there are two different vectors. They are mapped on the same vector, which is shown here in this example. Oh, thank you so much.